So this is the problem that presents, we would like to find the limit as x goes to c of f of x algebraically. And so our first step in that direction is going to be to develop some properties of the limit so that we can take limits and evaluate them algebraically for as large a class of functions as we possibly can. That's our goal. To prove these properties requires some machinery that we don't have. We won't have till Calc 2. Our Calc 2 students all end up proving these properties. I am going to present them and make an appeal to your intuition. I'm going to make them plausible for you, but I'm not going to prove them. It's one of the very few times in this class where I do this, where I say, here are some properties, they're true just because. Math doesn't normally ordinarily work like that. I have to do it only because we don't want to do a whole lot of computations with deltas and epsilons. Okay. So, here we go. We're going to have two properties that directly evaluate limits. And my first property is this. We call it the constant rule. And it says that if f of x is any constant function, in other words, one that does not change when x changes, then there's only one possible value for that limit, and what would that value be? Not 0. If f is a constant function that does not change as x changes, give me a constant, Will. 5. So if f of x is equal to 5 for all values of x, then what is the limit as x goes to c of 5? It must be 5. That's right. This is our constant rule. The limit as x goes to c of any constant is equal to that constant. And if I look at y equals k, and I consider the limit as x goes to c here, I think it's really obvious that no matter what x's I pick, I'm going to get y values that are not only arbitrarily close to 5, heck, they are 5. That's as close as you can possibly get. Therefore, the limit of a constant is that constant. That's our slogan, constant. This is the form that you want to have down in your mind for the constant rule. And we'll use that form. We'll apply it in various circumstances. We're also going to have a linear function rule. And our linear function rule is going to take a look at linear functions that are not constant. And I'm just going to assert that for linear functions, which are nice and well behaved, then the limit as x goes to c of that linear function is simply the value of the function at that point. In other words, we can evaluate the limit of a linear function by directly plugging in. Why? Intuitively, because linear functions are continuous. And therefore, what happens at that point matches what happens around the point c. What's the equation for a linear function? You all know it? X plus b, that's right. And so we'll express our linear function rule like this. The limit as x goes to c of any linear function is simply equal to the value of the function at that point, c plus b. I'll take a moment to just show you, in case it's not clear, how this might work. Here I have the limit as x goes to 1 of 4x minus 2, and I consider, hey, that function is a linear function. So I bust out my linear function rule and say that this limit is immediately 4 times 1 minus 2, which is 2, No graphing calculator required. Isn't that nice? Now, you have to check for a linear function before you can use the linear function rule. If you foolishly just say, hey, it worked for a linear function, so it's going to work for every function, you're going to have a bad time. So you have to check for a linear function first. Now, we're going to learn a whole slew of properties that allow us to break down complicated limits into simpler ones. All of these properties are very intuitive. So I'm going to kind of fly through them, but they are all going to come down to the same thing, which is that the usual functions you know, plus, minus, times, and divide, the usual operations that you know, plus, minus, times, and divide, preserve limits. That's it. So here we go. We're going to have a sum rule. If I have two functions, f and g, added together, then the limit of that sum is the same as the sum of the limits. The limit of the sum is the same as the sum of the limits. And the same kind of logic applies to differences. The limit of a difference is the difference of limits. Just like so. And products. The limit of a product is the product of limits. Like that. Now, this product rule is a rule that now helps us to evaluate some limits that we couldn't evaluate before. Let me show you an example of that. Suppose I want the limit as x goes to 3 of x squared. I do a quick check. Is this a constant function? No. When x changes, x squared changes. Is this a linear function? It is not. Can I rewrite this as the product of two functions? Is x squared a product? Yes. What does it mean to square something? It means to multiply by itself. So limit as x goes to 3 of x squared is the same as the limit as x goes to 3 of x times x. And that's simply rewriting squaring for what it is. And now I have a product, which means I can use the product rule. And the limit of a product is the product of limits. Here's my product rule for limits. And now I have two different, well, same linear functions. What is the limit as x goes to 3 of x? It's 3. That's a linear function, and I can evaluate that by direct substitution. So that I get 3 times 3, which is 9. Now we notice in passing that if I had directly substituted x equals 3, I would have gotten that same value 9, right? But we're not really sure if that's an accident or if that is going to happen every time. So you cannot just willy-nilly go directly substituting until you are positive that we have some rule that allows us to do that. See what I'm saying? So there's not going to be any shortcuts with this. You're going to have to work out the limit properties at first, and then we'll develop some shortcuts along the way.
Wait, I have a question about one of the properties. It's
Sure.
the simplest one, but I don't understand what the constant rule is trying to do.
Yeah, what the constant rule is saying is if I have something like the limit as x goes to 5 of 17. Now the function f of x equals 17 is very boring. Whatever x you give me, I give you 17.
Oh.
then this limit must be 17.
That makes sense.
Yeah. Good. There's a special case of the product rule called the constant multiple rule. And sometimes that's done as a separate rule. And it says this. If you have a constant times a function, then the limit of a constant times the function is simply the constant times the limit. And if you look really closely here, this is actually just a special application of the product rule, is it not? Because the limit of the product is the product of limits, but what is the limit as x goes to c of a constant? It's just that constant. So if you apply product rule, followed by constant rule to the constant multiple, then you get exactly this. But the way students like to think about it, and it's not a bad way of thinking about it, is that we have the effect of pulling out the constant to the outside of the limit. Does that make sense? Sure, that's right. So suppose that I take the limit as x goes to 3 of 5x squared. I look and I see a constant multiple right here, and so I pull out that constant multiple using the constant multiple rule, and I say to myself, so I've already figured out what the limit as x goes to 3 of x squared is. It's 9. And so I get 45 as the result. Does that help? Well, it's going to come as no surprise that we have a quotient rule. For limits. And that is that if I have the limit of a quotient, f over g, then that is the same as the quotient of the limits. Unless the bottom limit is what horrible value that we do not wish to see? 0, that's right. So there is a huge exception here. And that is that this rule fails when the denominator goes to 0. And I'll give you a really simple example of that from your previous Quizlet. We evaluated the limit as x goes to 2 of x squared minus 4 over x minus 2. If I attempt to use the quotient rule, badness happens. Can I use the quotient rule like this? Take a look at that denominator. What's it going to go to? 0, linear function, directly substitute. The quotient rule does not apply. The quotient rule is actually false for that case. But if I go to any other value, for example, I take the limit as x goes to 3 of x squared minus 4, then I can use the quotient rule because my denominator is not going to 0. And in fact, let me label the properties as we go down. QR, quotient rule, is that a fair enough label here? And in the top, I see the difference of two functions. So I can use the difference rule in the top, dr, to break down my big limit into two smaller pieces. In the bottom, I have what kind of a function sitting there? Linear function. So I can immediately use the linear function rule in the bottom to evaluate this with direct substitution. 3 minus 2 is 1. Okay. Linear function rule. Does it make sense what I'm doing here? And then I've already evaluated the limit as x goes to 3 of x squared. And this is what kind of a function? That's a constant function, so what's its limit? 4. And lo and behold, I have algebraically evaluated a limit that was fairly ugly. Does this make sense? What we're doing?
Can I write this down?
Keep it.
I missed some of the one that was wrong.
Yes.
What was,
What happens when I evaluate the bottom limit? The limit is x goes to 2 of x minus 2. What number do I get? I get 0. That's right. And because I get 0, that means that my application of the quotient rule here was wrong. Cannot use quotient rule when the bottom goes to 0. Sometimes I might not know that ahead of time, and I have to backtrack and I have to say, okay, this was the wrong way to go. Yeah.
What, I'm sure people probably asked you this before and it may sound silly, but what happened in that case? Would that not be that, say, if the limit of the top section was x to...
Tell you what, we only have a couple of minutes, and we're going to spend a whole day on stuff like this, very soon. So I'm going to just postpone your question. That's a great question.
and could you scroll down, please?
Uh-huh.
I love what you already know what I'm going to ask.
I've been doing this for a long time. Okay. Our final rule that is going to help us grade. Yes, sir.
How come I missed where you did the difference rule right there?
Yes.
How come it went over 1 and you got 2?
Ah, what type of a function is this?
It's,
It's linear, and we have a linear function rule. So I went straight there.
okay.
Okay? Our last rule is the power rule for limits. And it is also straightforward. If I have some power of f of x, then the limit of a power is the inside to that power. This is really nice because it allows us, for example, to immediately compute powers of x, limits of powers of x. So, for example, if I have the limit as x goes to 2 of x plus 1 to the 17th, ugh, scary. If I wanted to write that as a product, it would be awful, right? I'd have 17 different factors. But if I use the power rule, I can immediately write that as the limit as x goes to 2 of x plus 1 to the 17th power, using the power rule. And what type of function is that sitting on the inside? Everybody all together, loud and proud. What type of function is sitting there on the inside? It is linear. How do you know? Because it has the form of a linear function, mx plus b. And therefore, I can immediately evaluate the limit by direct substitution. Do I want to multiply out 3 to the 17th? I do not. So these are the limit properties. And the way in which we will use them is we'll take big limits, awful limits, and we will break them down into smaller pieces. I think I'm going to do, I'm getting the sense from you guys you'd like to see a couple of examples.
Yeah.
I'm going to do a quick video that will do a couple of examples that will show you how these limit properties might be used. Okay? Let me pause at this time.